My dear friends, welcome to Rajashekhar classes on Applied Data Science with Python. This is lecture number 382. In this lecture, we will try to understand support vector regression. Support vector mission SVM classification. SVM, when it is used for classification, it is often called as SVC. SVC means support vector classification. When it is used for regression, what is regression? Regression means yi belongs to capital R. Just see, in support vector classification, yi belongs to +1 or -1. +1 means positive class, -1 means negative class. Whereas in support vector regression, your yi belongs to our real number system. We can do regression using support vector missions. Formulation changes slightly. Let's look at the mathematical formulation. What is this mathematical formulation? This is linear form of support vector regression. Minimization w comma b 1 by 2 into norm w square w such that yi minus w transpose xi plus b less than or equal to epsilon, w transpose xi plus b minus y less than or equal to epsilon, epsilon greater than or equal to 0. What is this? 1 by 2 into norm w square. This is like your regularization, isn't it? What is this yi? Yi is actual value. This yi cap is predicted value. This is actual value minus predicted value. What is predicted value? W transpose xi plus b. Isn't it? That may be yi minus yi cap less than or equal to epsilon, or you can say this one also is there. Yi cap minus yi less than or equal to epsilon. This is yi cap, isn't it? Minus yi less than or equal to epsilon. Yi is my actual value. Yi cap is my predicted value. My model basically consists of what it consists? It consists of w comma b. I want the error between my actual value and my predicted value, that is yi minus yi cap, yi minus actual value minus predicted value. It must be less than or equal to epsilon. Similarly, I want yi cap minus yi less than or equal to epsilon. Here, what is your epsilon? Epsilon is hyperparameter. In the case of SVR, your hyperparameter is epsilon. In the case of support vector regression, epsilon is hyperparameter. What we are seeing here is the simplest formulation. This whole thing can also be kernelized. This entire thing can be kernelized, isn't it? This whole thing can also be kernelized to fit. It can be kernelized to fit any shape. So, for example, if it is not kernelized, what happens? If it is not kernelized, let me say this diagram. This is my x. Let me say, yes, just let me choose some other color. Yes, let me say this is my x, this is my y. You will only be able to fit planes. You can only able to fit planes or lines, isn't it? If you have any curve like this, for example, if you have any curve, this is linear SVR, isn't it? Linear SVR is this one, linear lines. Kernel SVR means what? What is kernel? If you have any curve like this, you can fit with kernelization. That's why I am writing here kernel SVR. You can fit with kernelization because kernel SVR can fit any non-linear shape. While linear SVR, this is the linear SVR. While linear SVR can fit planes or lines. Here epsilon is your hyperparameter. And what does epsilon says? Epsilon, if it is low, just let me say, if epsilon, if it is low, This is very important. If epsilon is low, what does it mean? It means your errors are low. Epsilon is low means what? Errors are low on training data, isn't it? Which means your chances of overfitting increase. Similarly, if epsilon is high, your errors on detrain could be higher, isn't it? Could be higher, which implies underfit. Underfit may increase. Let's look at one simple example. Just see, this is the diagram which I collected from Wikipedia. If we go to Wikipedia, support vector missions, there is a nice article. This is again using, just see, this is using RBF kernel, isn't it? If you don't know what kernel to use, always use RBF because it behaves like a KNN. So RBF SVR behaves like KNN regression, isn't it? Now, how does KNN regression works? Given a query point, let me say, how does it work? Given a query point xq, given a query point xq, let me say xq is a query point, pick the k nearest points. These are the nearest points, k nearest points, and take the mean value. It roughly works very similar to RBF SVR, isn't it? Suppose, just let me go back, let me go to that particular diagram. Suppose this is the diagram which I collected from Wikipedia. Suppose these block dots, just see, these are the block dots, isn't it? Let me assume he is saying, what is this block dot here? Block dot means data, isn't it? Suppose the block dots are my points. The blue line is actual function. Just see, true means what? This is blue line. This blue line is actual. This is actual function, of course, with some errors, isn't it? So certainly it is with some errors. Of course, with some errors. Look at as my epsilon increases. We have plots for epsilon equal to 0.01, epsilon equal to 0.1, 1.0, 2.0, isn't it? As my epsilon increases, when epsilon is very small, let me consider epsilon equal to 0.01. Then I get brown line here, which is very similar to the actual line. Just see, this is the brown line, which is very similar to the actual line, isn't it? But it does start making mistakes. Just see, in this region, but it does starts making mistakes. The brown line here, isn't it? Start making mistakes because there is no data. Just see, in this region there is no data. It start doing mistakes. If you look at this region, the actual curve is dark blue. This is actual dark blue curve, isn't it? As there is no data here, it starts misbehaving and very far away from the actual curve, isn't it? What about in this region, your blue line? Just see, in this your blue line, just see, in this particular region, your blue line and brown line are almost overlapping, except here, except this portion, isn't it? Except this region. If epsilon is small, you could overfit to the training data. That is important. If epsilon is small, that's what we were discussing. If epsilon is small, you could overfit. As epsilon increases, when epsilon becomes very large, for example, epsilon equal to 2. Epsilon equal to very large means this line, this red curve, this one, isn't it? When epsilon equal to this red line almost becoming a straight line. So when epsilon is small, it overfits to the training data, and when epsilon is large, you will underfit to the training data. Underfitting basically means, just let me draw one simple curve. Let me say like this. If this is my actual function, let me assume this is my actual function, this is my x, and this is my, let me say, this is my y, isn't it? Overfitting basically means if there is one extreme point, this is one extreme point, isn't it? If there is one extreme point, just for that point, everywhere else it works. One outlier change the shape, This is the case. Just see this. If this is the case of my overfit, this is my original function. Because of this particular outlier, overfitting means what? Just see. Just because of this outlier, this curve passes through like this, isn't it? This is original function. This is overfitted function, isn't it? One outlier changed the shape. Because of this particular outlier, this shape itself changed, isn't it? One outlier changed the shape. This is the case of my overfit. This is my original function. This is my original function. This is overfitted function which is passing through the outlier point, isn't it? This now, and what does underfit means? Underfit basically means, just see this one. This is super underfit. This is superly underfit, because I am not taking all the data into consideration. I am just taking the average value type stuff and fitting a line here when you have much farther away from the original thing. If outliers are impacted, if outliers are contributing to the change the shape, you are overfitting. Because of this outlier, you are changing the shape. That is overfitting, isn't it? Representing a sine wave. Original curve is just like sine wave with a straight line. You are representing a sine wave. You are representing a straight line, isn't it? That is underfit, isn't it? Representing a sine wave with a straight line is super underfit. It is super underfit. This is how overfit underfit works in regression, and that's what here exactly shown. Just that's what we shown in Wikipedia also. You have sine wave as epsilon increases, you are underfitting, isn't it? As epsilon is increasing, you are underfitting, because as epsilon increases, you are underfitting because you are trying to get almost a straight line. Just see this. That's what happens for regression, isn't it? This is related to underfit. This is related to overfit. This is the original curve. This is SVR. SVR means what? Support vector regression. Just go through these things. If you have any difficulty, please keep a comment. Thank you very much. Just try to understand this with the help of this particular Wikipedia page, where it is explained nicely what happens for epsilon equal to small value, for what happens for epsilon equal to large values. For epsilon equal to 0.01, you can see overfitting. Epsilon equal to 2.0 means it's underfitting. Underfitting means you are almost getting a straight line. Thank you very much.